Greetings from Middle East Technical University, Ankara, Turkey. I am Akif, this year's team leader, and today me and my teammates are going to present our new rover. METU Rover is a robotics team founded in 2018 that combines mechanical design, robotics, and space technologies. The team currently consists of 33 undergraduate members from various departments. We operate through 4 core sub-teams: mechanics, electronics, software, and science. Competing in both European and Anatolian Rover challenges, the team established its commitment early on by winning the Jury Special Award in its first European Rover Challenge. He later placed 7th in the Anatolian Rover Challenge 2022 and competed as a finalist in the European Rover Challenge 2024. Most recently, the team achieved 5th place at the Anatolian Rover Challenge 2025.
Our laboratory is our main workspace where we conduct both the design and production processes of our vehicle. Meanwhile, our container serves as the primary workspace for manual production activities. We also have a room where we carry out research studies.
For our mechanical system, like the ARC, the chassis and the suspension, our goal this year was very clear. We focused entirely on making the rover more reliable, simpler and easier to assemble. Our rover chassis is built around the hybrid architecture, carefully balancing structural rigidity with rapid assembly.
The mainframe utilizes modular aluminum sigma profiles. However, for high-stress areas, we integrated topology-optimized CNC supports, along with the lightweight 3D printed joints, to achieve exceptional strength-to-weight ratio. The total mass of the rover is 62 kg, designed with a high ground clearance of 400 mm. The vehicle is highly compact, yet optimized for aggressive maneuvers. To tackle unpredictable and uneven terrain, we implemented a passive rocker suspension systems. This geometry ensures that all wheels remain in continuous contact with the ground, allowing us to safely traverse rocks and climb slopes up to 40 degrees without losing stability. Moving on to mobility, our rover features a fully independent 4-wheel drive and 4-wheel steering architecture. For the steering modules, each wheel is controlled by a DC motor paired with a 25:1 ratio Verne gearbox. We specifically choose this transmission for its inherent self-locking capability. This crucial feature locks the steering angle in place. It prevents external forces like hitting rocks or sudden power loss from alternating wheels heading, ensuring maximum directional stability on rough terrain. For traction, we utilize custom impact-absorbing TPU wheels and grazers, which are inspired from NASA's rover. Combined with our independent steering, this setup grants the rover omnidirectional maneuverability. We can perform zero-radius turns, grab walk, and accurately approach the objective station from any direction with a precision.
Rather than drawing inspiration from specific industrial models, we developed an original 5-degree of freedom manipulation system focused on simplicity and guaranteed reliability.
To handle heavy loads, the shoulder is driven by a linear actuator, providing 1000 newtons of force. At the elbow, a custom 8:1 ratio PETG planetary gearbox delivers 70 Nm of torque, optimized for both reliability and ease of production. The wrist utilizes a direct drive configuration to eliminate backlash, leading to a compact bevel gear differential gripper capable of applying 5 kg of grip force. With a maximum reach of 1.2 meters and a 5 kg payload capacity at full extension, this system provides the precision and strength necessary for the most demanding intervention tasks. At the end of our manipulature, we utilize a custom dual-motor bevel gear differential gripper. Unlike standard linear grippers, this compact mechanism provides exceptional versatility. It delivers a strong 5 kg of grip force to securely handle heavy tools, while maintaining the millimeter precision required for delicate operations like flipping switches. To control this 5-degree of freedom architecture, we developed a comprehensive 2D kinematic model to map out our precise reach envelope. This ensures safe and accurate trajectory planning without colliding with the rover's chassis. Additionally, a dedicated and effective camera provides our operators with a clear, first-person perspective, maximizing depth perception, and control during complex servicing missions.
For the science mission, we engineered a highly reliable deep soil sampling system capable of collecting core samples down to a depth of 30 centimeters. The core drill is driven by a DC motor, providing the necessary rotational force to cut through hard-packed and unpredictable terrain.
As the electronics team, we are responsible for managing all the power distribution and connection networks on the rover, successfully linking every single component from the data sensors to the main auto-control systems.
To avoid the limits of standardly made parts, we designed our own custom PCBs. This special hardware makes sure every part of the rover works with great efficiency, full control, and exact detail.
To protect the sensitive electronics from electrical noise, we use a dual battery system. The logic battery powers the computers, sensors, and communication system, while the main battery powers the motors and other high-power components. By separating these two power lines, voltage drops and noise from the high-power side do not directly affect the logic side. This helps the rover stay stable and reliable, especially during demanding operations.
As the software team, we are responsible for communications, control, and autonomy of our rover. This year, our main focus is redundancy and reliability. Our rover's distributed architecture relies on robust communication systems and advanced software integration.
Our system is built around the Jetson NX, acting as a central computer, which networks with 12 Raspberry Pi Pico microcontrollers. We use an Ethernet-based architecture to link these subsystems.
For actuation, our control methods depend on the motor type. The brushed DC motors run on custom PID controllers via the Picos, utilizing magnetic encoder feedback to maintain precise control. The brushless motors have built-in drivers, so the Picos interface with them by transmitting position encodings over a CAN bus. Across all these subsystems, we implemented an automatic software level E-stop that cuts power instantly during stall conditions to prevent mechanical failure. At the ground station, we rely on NASA's OpenMCT framework to manage raw ROS2 telemetry. The dynamic dashboard centralizes real-time health metrics and our WebRTC video streams.
Our autonomous navigation stack is built on ROS2 Humble, utilizing the Navigation 2 framework for dynamic path planning and obstacle avoidance. For spatial awareness and SLAM, we run RTEP map to process the depth and visual odometry data generated by the Z2 stereo camera.
As METU Rover science team, our primary objective is to examine the astrobiological potential and geomorphological structures in the region, Athabasca Valles. Our workflow begins with a literature review to establish geological context. We then transition to advanced remote sensing, utilizing JMARS for geospatial data integration, QuickMap for high-resolution morphological assessment, and USGS databases for stratigraphic mapping. We execute a targeted 4-stage experimental suite. We will use hydrochloric acid to detect carbonate presence, and hydrogen peroxide to test for oxidative potential and enzymatic activity. To search for biosignatures, we deploy the BURET test for protein detection and LUGOL test for organic complex identification. We will also use the color sensor and a pH sensor to further strengthen our experimental results.